Okay, we are now recording. Let's see. I think we have just a little bit of verbiage to cover first, so let's go to the other slide first and go from this one. Okay. First thing I want to know is, are there any questions from what we've covered so far? Okay. Yes?
I started working on the assignment that you gave us, and some of the problems I had a little hard time understanding. I sent you an email, but I didn't get a response about it.
Okay. I have been stacked to the gills, and I've been trying to catch emails when I can, but every time I open them, there's just a ton more out there, so I missed it. Sorry. What? Any specific problem?
Well, yes, sir. And I wasn't sure if you were going to go back over. I don't want to make you skip past something.
No. What's your question? Yeah, sure. Anytime is a good time to ask questions.
Okay. For example, some of the problems, they wanted us to round, but I was trying to figure out, like, when would you round and when would you not round?
Okay.
For example, like number 21.
Okay. I take it this is on page 131, maybe?
This would be the 21 on page 128.
Oh, 128. Okay.
Yes.
Okay. And which one? 29? 21. Okay. All right. A forklift has a mass of 971 kilograms. So they tell you what that is. That's the mass. Okay? 975 kilograms. That's a great unit for mass, kilograms. Okay? What force, so we're looking for force, that's the unknown here. What force must be applied to give an acceleration of 2.5 meters per second squared? 2.50 meters per second squared. Now, by the way, that is an incredibly large acceleration. Not a very realistic problem, especially with a forklift. That means you're increasing its speed 2.5 meters per second every second. You're not going to be able to maintain that very long. You would be soon really large acceleration. So that would be pretty tough to do. But let's do the problem. How would we approach it? What is force in terms of mass and acceleration? It's mass times acceleration. Okay, so what we do is take the mass, 975 kilograms, and multiply it by 2.50, the acceleration, meters per second squared. And what does that give us? It's not one I particularly want to do in my head. 2,477.5? 37.5. And that would be what units? Let me get, is this?
It's Newton.
Okay, you're absolutely right. It's newtons. Let me get,
My assumption was that.
right, okay. Yeah, wait, just a second. Get your name, please.
Caleb.
Second?
Caleb.
Okay, Caleb, got it. All right, good deal. So we're only missing Vega today. I think is the only person out. No, well, Fiona Saunders, which we haven't seen from the beginning, but of the ones who have been coming, Vega. Okay, now, and you said this was in newtons. Okay, now, your question was, when do you round and when do you not round? You always round. Okay.
I thought we would say 2,438.
Okay, all right. Yeah, okay, here's what you do. How many significant digits here? 3. How many significant digits there? 3. So therefore the answer can be no more than 3 significant digits. So you count 1, 2, 3 digits. look to the right. That's a 7. That's greater than 5. Round the 3 up. That would be approximately 2,440 newtons. See, this 0 is not significant. Okay, so that's why it's 3 significant digits. Okay, yeah.
And that's what I was wondering when that
Yeah.
rule kicked in, and I
Yeah.
guess that's where the disconnect was.
Yeah.
Okay.
Yeah. The rule's always there, always round, and be sure you've got as many significant digits coming in as you had going out as you had coming in. But if that 0 hadn't been there, that would have only been 2 significant digits. Then you would have said 2,400 newtons. Okay, but because the 0 was there, see, zeros after a decimal point are significant. Zeros before a decimal point typically are not. Okay. Good deal. Any other questions? Good question, by the way. Excellent question. Any other questions? All right. If not, if there are, please ask. Always ask questions. Okay, we're at the top of page 132. We're in chapter 5, force, and the section we're in now is 5.4, friction. Friction is a type of force. Can anyone tell me anything about friction that we learned before? Friction is a force that always supports or opposes the motion. Say again? I can't hear. Okay, friction is a force that always supports or opposes the motion. Opposes, always opposes. Okay? Now, we're about to hit 2 types of friction. Okay? One of these is called static friction. Okay. Now, static friction is the force that opposes the start of relative motion of 2 objects. Okay, notice that, opposes. The start of relative motion of 2 objects. Okay. Now, I guess they say in contact with each other. Okay. Now, I'm going to pull on this desk. Pulling on the desk and being opposed by static friction. Which direction is the static friction? That way, because I'm pulling this way, it's opposing my motion. Okay? Fortunately, this is up with, nope, it's not quite against the wall. So I'm going to push on the desk. And I am pushing, table. I am pushing, but it's not moving. What's the static friction doing now? Opposing me in this direction. It always opposes the motion that you're trying to make. Now, this time, I'm just going to pull a little bit. Okay? How much static friction is pulling against me? That same little bit. If I pull a little bit more, oops, I've got to move there. A little bit more, it's opposing me a little bit more. It varies with what I'm doing. Otherwise, if it wasn't exactly equal to mine, the thing would be moving. Okay? And when I push a little bit, it's pushing back at me a little bit. A little bit more. As long as it doesn't move, then it's pushing back a little more. So you see, static friction is sort of a variable friction. It only is enough to keep the motion from happening. That's what they mean by the force that opposes the start of relative motion of 2 objects in contact with each other. Now, where is that friction? It's between the feet and the floor. The feet of the table and the floor. Okay, that's where the friction is. Okay, those are the two objects opposing each other. That's static friction. Okay. I've never heard it called this, but this book says it's sometimes called starting friction, which is an okay thing to call it too. I like static better. That's more general. Once the touching objects are in motion, though, relative to each other, the friction is generally less and is called kinetic friction. Okay, kinetic friction, sometimes called sliding friction, and I have heard that one before. Now, what does the word kinetic mean to you? Moving. Something is moving. There's a whole field of study called kinesiology. That is a study of motion. Okay, a lot of have a nephew who majored in kinesiology, and he got into physical therapy because it is the study of motion. Okay, so kinetic means moving. Later, next chapter that we study will be covering energy, and there's two types of energy. Well, there's many types of energy, but one of the types is kinetic energy. That's the energy of motion. So kinetic energy is when relative motion, okay, after relative motion has begun. Okay. Now, just wonder if this has ever happened to you. Okay? You'll be pulling on something, pushing on something, and suddenly it gives way, and it seems like it's easier to pull with. In fact, you almost fall backwards because it now is moving more freely. The table just did that, you know. I had to ease up on it to keep it from coming any faster, okay? That's because kinetic friction is usually less than, sometimes equal to, but less than the maximum static friction. Okay, remember, static friction was variable. It could be a little bit or a lot. Once you overcome the static friction, then the kinetic friction is usually less than static friction. And they used to use that a lot in the cartoons when something would finally move and the person would fall down and was pushing you. I didn't want to do that for you today. But anyway, that's kinetic friction. Generally less than the maximum static friction. Now, is friction a good thing, a bad thing, or sort of an indifferent thing? It can be good. When is friction good? When I was driving over here today. Yes, when I wanted to stop, it was good that friction let me stop. Not only that, when I wanted to go, it was good that friction allowed me to go because the tires pushing against the road, if there had been no friction there, it would just been like that. I wouldn't have gotten anywhere. Or when I tried to stop, hit the brakes, and it just slides right on into the next car or whatever. Yes, friction is good in that case. When is it bad? What's that? Well, that's all right. Say something. How about in your engine? You want friction in there? Oh, no. That's bad in the engine. So on the way over, friction was good and bad, okay? Because in the engine, you want things to move past each other without friction. Because friction produces heat, and that's one of the reasons you have the oil, the water, and everything else to control the oil to control the friction, the water to dissipate the heat, okay? It's both necessary and hindrance in our everyday lives. We wouldn't be able to walk, drive, swim, or anything else if you didn't have friction. But then, too, pushing tables or pulling things around, far worse if there's a lot of friction. Okay. Here are 3 characteristics, you might say, of friction. Okay. This is all on page 132 if you got your books. Friction is a force. This is sort of repeating what we've already said. Friction is a force. Okay, what units would be measured in? Give me at least one. Newtons, exactly. Another could be, in the U.S. customary, forces are measured in. I stand on the scales. Okay, kilogram is a mass. Remember we had that in the last problem. Pounds, exactly. Pounds is the U.S. customary unit for force. So friction is usually in newtons or in pounds. Okay? So friction is a force that always acts parallel to, I'm going to just put two parallel lines there, to the force, to the surface in contact. Okay? And opposite to the direction of motion, which we've already said. Second? I can't hear you.
Parallel.
Parallel? How do you...
I was asking, was that?
Yeah, that stands for parallel. I just am really lazy with writing and use symbols whenever I can. Okay? If there is no motion, friction acts in the direction opposite any force that tends to produce the motion, just like I was doing here. So let's think about when I'm in the car, I was driving, and you said when I went to stop. This is easy to get confused on. I was going toward the stop sign, and I wanted to stop going toward the stop sign. Friction tends to make me go toward it, you know. So it's a rather bizarre thing, always acting opposite. So if I'm trying to push, it's trying to pull. If I'm trying to pull, it's trying to push against, okay? So it's a force that always acts parallel to the surface in contact and opposite to the direction of motion. That's the first thing. Let's go, yuck. Okay, we're going to, when we come back, this won't be here anymore, but we'll continue. But let's go to this slide. And this illustrates this. And this is what I was trying to do with the table. Okay? If I'm pulling on this crate across the floor here, maybe that's a rough, gravelly kind of floor or something like that, I exert an effort this way, friction always is parallel to the surface, okay, and always opposes my motion. Now, if I've got twice as much mass there, so twice as much weight that I'm trying to pull, my effort force has to be greater, friction is greater. This is all in the static friction form because these two are equal to each other in both cases. So that's still static friction. If finally I had gotten it to move, then the effort force would be greater than this, but friction is still always working against and always parallel to the surface. Okay? So that kind of illustrates the first one. And it kind of illustrates the second one too. I may go on and put the second one here. Now, let me go back to the other. This will have already disappeared. And I've got to get my pen back. Okay. Now, the second characteristic friction is one we've already said before, static friction. They say, I kind of have a little bit of question on this. They say is greater than kinetic friction. And the reason I have a little bit of hesitation with that one is I usually see that says greater than or equal to. There are a few surfaces that you can hardly tell the difference between static and kinetic friction. They're almost equal. But they never is static friction less than the kinetic friction. That just wouldn't work. Okay? And the third one, and I think I already described that one to you, friction increases as the force between the surfaces increase. Okay. Increases. Okay. Here's a real simple example of that. If you rub your hands together without pushing on them much, you probably don't feel a lot of heat. But if you push on them and rub them, you feel quite a bit of heat. The heat is created by the friction. The greater the force between the two surfaces, the greater the friction. And if you go back, which I was just starting to do, now I'll lose those two, but it's all right too. I guess I could save those, but then they're a pain in the neck to get rid of them. Okay. If we go back a couple of slides, this illustrates that. If you had more weight on top of this, then these things tend to fall down into the grooves even more so, and they're harder to get out of the groove, because this is what's happening on a microscopic scale. The little peaks and valleys get interwoven here, and it makes the friction even greater. So if there's a lot of force here, then it's even harder to move that across, because the points go down into the valleys, and then they're hard to move one way or the other. The more force you do, the deeper they go into the valley, and the harder and harder it is to do. Okay? So that's what they were referring to there. And this one, the greater the force on the surface, because you have twice as much weight here on this surface here, that means you even have a greater effort force, but a greater frictional force as well. Okay? Both of those illustrate that. Now, I want to go back again to something we talked about before, and that was a normal force. Remember that? The force of gravity on the brick here is pulling down, always toward the center of the earth. But the reason the brick's not falling through the table surface is pushing up on the brick with a force they call the normal force. Normal meaning perpendicular to. So the next statement that we have refers to that normal force. And here's what it is. Okay? The force due to friction, let me get my pen back. Force due to friction. Now this book uses capital F for just about any force. What does F sub G stand for? F sub G. Remember what that one was? Force due to gravity. That's your weight. Force due to gravity is weight. F sub N, normal force. F sub F, frictional force. The capital F is force, and the frictional force is equal to this symbol, mu. That's the coefficient of friction times the normal force, the force that's perpendicular to the motion. Okay? There is your basic equation for the frictional force. It's equal to mu, which is the coefficient of friction, times the normal force. Okay? So this is frictional force here. This is the coefficient of friction. And this is the normal force. Now the normal force is the force of the floor up on the crate. Parallel or perpendicular to the surface of the floor. Because remember, the friction is always parallel to the surface of the floor. Okay? So that's the normal force here. F sub n here, this would be an even greater F sub n because it has more weight down. Okay. Now, this coefficient of friction that I've written here, the mu, is the ratio of the frictional force to the normal force. So you could rewrite this as mu is equal F sub F, frictional force, to the normal force. Okay? And of course, you could write it one more way, and what could that be? Here you have a multiplication, here you have a division. Is there one other equation we could get out of this? Yeah, do F sub n is equal to F sub F over mu. Okay? You just flip them. Okay? And again, you could do this with your triangle or circle. I kind of like triangles better. That's your dividing line. That's your multiplication line. And here we have F sub F is equal to mu times F sub n. That's this one. And then if you cover the mu, you get F sub F over n. That's that one. Or cover F sub n, and you get F sub F over mu. That's that one. Or cover this one and you get mu times F sub n. So you can do that with circles or triangles. But that's the relationship. Now, the coefficient describes how rough or how smooth the two surfaces are when they're in contact with each other. The higher the coefficient of friction indicates rough surfaces, whereas a lower number indicates smoother surfaces. Okay? Now, in the table in the book, which I don't think they show here, I wish they did. Do most of you have a book? I see several books out there. If you don't, try to look on with someone who has one. There is a table, 5.1, in your text on top of page 133 that gives some of these. Notice there are two different coefficients of friction. Okay? Now, the book doesn't do a good job of this, I don't think, but most books will have mu sub S, static friction, and mu sub K, what would that stand for? Kinetic friction, exactly. Two different coefficients of friction. Which one you think is usually larger? Static, exactly. Look at the table in the book and you'll see that. Steel on steel, static friction, 0.58. Kinetic friction, 0.20, less than half. Okay? Steel on steel lubricated, now there's a case where they're the same. If you've lubricated that well, you have almost, you cut the friction big time, and generally the static friction, kinetic friction, hardly any difference. Because if that's well lubricated, you push on it and it just moves. There is hardly any static friction involved. Okay? Glass on glass, 0.95 for static, 0.40 for kinetic. Again, less than half. Hardwood on hardwood, 0.40 for static, 0.25 for kinetic. Not quite half. Okay? Steel on concrete, they don't even give a static friction. I'm not sure why, but 0.30 for kinetic. aluminum on aluminum, 1.9 for static, and they don't give one for kinetic. And here's kind of why. This aluminum on aluminum. Aluminum is a fairly soft metal, okay? Statically, it's going to give you a lot of resistance. That's 1.9. You know, that's greater than steel on steel, glass on glass, any of those others. But if you start doing kinetic friction, aluminum, since it's sort of a soft metal, the peaks on the aluminum will dig into the soft aluminum either on the top or bottom of it and actually dig deeper. So they don't even refer to aluminum on aluminum for kinetic, because sometimes that would actually come up greater, and that violates their rules, so they don't even show that. Rubber on dry concrete, 2.0. That's important when you're driving the car, right? That's static. Kinetic, 1.0. Exactly half. Now, what's the ramification of that? And if you ever had driver's ed, they probably taught you this. Or if you know anything about cars, you might understand a feature they brag on. And that is, if you start skidding, what should you do? Lift off the brake and sort of pump it, because you want to reestablish static friction and get away from the kinetic friction, because the kinetic friction is half as much. And actually, I've had it happen to me once. It was a bad situation. Many years ago, more than 2 decades ago, I was teaching part-time at Jeff State, and I was driving down for my first class, and it just poured rain. And we lived over in Southside Birmingham. I usually looked at the traffic to see how bad the interstate was backed up, and I'd go one way if it was backed up, or I'd get on the interstate if it wasn't. And I thought with the rain we just had, the interstate would be at a standstill. But it wasn't. It was moving along pretty well. So I said, well, I'll go and get on. So I got on the interstate, and as soon as I crested the first hill, there I saw nothing but a band of brake lights in front of me. And the car in front of me veered over and filled up the last spot that it could go, and I hit my brake. And it felt like I sped up, because I went from static friction, which was sort of trying to brake me, to sliding friction, which was less, and I did. And I did clip the back of the car in front of me. Made me so mad, but it was hydroplaning is what they call it. You lost your friction altogether. Okay? So rubber on dry concrete, static friction. This was wet concrete. Notice it's 1.5 static friction, 0.97 kinetic friction. That's what I hit, and I actually sped up. Aluminum on wet snow, 0.4 for static, 0.02 for kinetic. Okay? Now, why would that be important to anybody in particular? Skiing, exactly. You want as little friction as possible until, of course, you come approaching a tree or something, or at the finish line, and you're trying to get it to stop. So they turn the skis sideways so you get as much surface area. When they're like this, you have very little surface area, or as little as possible. So you're going downhill as fast as you can. When they twist like this and bend them up, you're trying to get the maximum amount of static friction that you can to get you to stop. Okay? Aluminum on wet snow, that we just said that one. Steel on Teflon. Here's another case. Kinetic is no better than, static is no worse than kinetic. It's 0.04 on both of them, because Teflon is that non-stick material. Remember, y'all wouldn't remember when the pans didn't have Teflon, and your eggs would always stick. Everything, you had to put lots of grease in them. Teflon, you almost need any grease at all. The pancake just flip right over. Okay. Now, Just a little examples here. In general, to reduce kinetic friction, use smoother surfaces. Okay? The rougher the surface, the more the friction. Use lubrication to provide a thin film between the surfaces. Use Teflon to greatly reduce friction between surfaces when an oil lubricant is not desirable, such as electric motors. You don't want to get oil or any other liquid in an electric motor. And substitute rolling friction for sliding friction. Rolling friction is a resistance that occurs when an object, such as a wheel or a tire, rolls on a surface, usually much smaller than sliding friction. Use ball bearings, roller bearings, greatly reduces friction. So that's what they do. All right, ready for example 1, bottom of page 133. So let's get out of this slide, go back to our plain slide, and let's do example 1. A force of 170 newtons. Let me get my thing back up. So let me get my pen back, right? Every time I change, I have to change the pen. Okay, here we have a force. We don't know what kind of force it is, so we'll just make it F for now. Force of 170 newtons. Good unit for force? Absolutely. Newton's a SI unit for force. Is needed to keep a 530 Newton wooden box sliding on a wooden floor. Okay? So a force of 170 newtons is needed to keep a 500, so what's this 530 Newton box? What would that be? What force is that? When you just see something so much like, okay, that's going to be related to the normal force. It's actually the force due to weight. I'm sorry, I think I said before F sub G. I think this book uses F sub W. That's right. Sorry about that. F sub W, force due to weight. Okay, that's the weight of the box. And you're absolutely right. This is also going to be the normal force. So you're right on that. And a force of 170 newtons, that's going to be your, is necessary to keep it moving. So that means that's the force of your friction. If you got to use that to keep it moving, that's what you have to use to overcome the friction. So this is going to be your frictional force. So it says, what is the coefficient of kinetic friction? The mu sub K is what we don't know here. And what do we have from before? I had to erase the slide. Sorry about that. What was that? What was the formula for mu sub K? Or any mu?
It's going to be the 170 divided by 530.
Okay, yeah, exactly. It's the frictional force divided by the normal force. That's the formula we used before, and this will be 170 newtons divided by 530 newtons. Now, just to make life a little easier, you can just cancel out the zeros because you're dividing both of them by 10. You also cancel out the units, newtons, because coefficient of kinetic friction is a dimensionless quantity. There should be no dimensions with it. So at 17 divided by 53, what would that be? To 2, because you see neither one of these zeros had a bar over it, so that meant you only have two significant digits. 0.32, no units, dimensionless quantity. And this was wooden box on a wooden floor, wood on wood, up above. Didn't we have that? Maybe not. Oh, hardwood on hardwood. They said about 0.25. This was about 0.32. This may be pine, not hardwood, so it might have a little bit greater coefficient of kinetic friction. Okay, let's see how the book did. 0.32, way to go. Notice that mu does not have a unit because the force units cancel out. All right. Now, remember the other thing I was saying, what you do when you start to slide in your car? You pump your brakes, trying to reestablish static friction. What do new cars have that sort of does that for you? ABS, anti-lock braking systems. And they talk about that in your little blurb here on physics connection. Since we're not going into that, you're not going into auto mechanics probably, you're going into sonography, then we'll leave that alone. But it's worth a read, and it's pretty interesting. The computer starts doing that pumping for you and eases off and stuff and tries to reestablish the static friction so you can have greater control of your car. All right, that leads to problem set 5.4. I think the back of the book has odd answers, right? So you could do any of the odd problems 1 through 7 and any of the odd problems 9 through 15. Now, there's another thing listed here, new technologies, hydrophobic metals, another way to help reduce friction. Teflon coatings are some of these, and they talk about some others here. Again, it's a hydro meaning water, phobic meaning fear of, so the metal tries to resist the water, okay? And that's what they show here. Water beads up on this metal rather than sticking to it, okay? Now, next topic here is total forces in one dimension, okay? Now, what we're dealing with here, remember from way back we said that forces were vectors. So when you're in one dimension, if you have a force this way and another force this way, they add. Force this way, another force this way, they subtract. When you have them like this, you have a mixed bag because vectors add and subtract differently from regular numbers. But when in one dimension, they either are going to be adding or subtracting. And that's what we're getting at here. And the little blue box says, when forces act in the same or opposite directions, in other words, in one dimension, the total or net force can be found by adding the forces that act in one direction or subtracting the forces that act in the opposite direction. Is that worth writing down? I'll be glad to do it if some of you don't have books. Do it? Okay. So I think I'll do it on, even though it's a new section, we got room, so let's write it here. Okay? When forces, I can't write. What's that? Okay, basically your test is made up of problems. Okay, so it's not so much the definitions, but in order to know how to work the problems, you need to know the rules. And this is one of the rules. Okay? So, no, you're not going to be asked to quote this phrase. Okay? You're going to need to know how to use this phrase in working a problem. What's that? I can't hear. Oh, yeah, this is 5.5. Oh, I'm sorry. I thought you said it was just going to be on the test. I'm so hard of hearing. It's pathetic. Okay. Yeah, sorry about that. This is section 5.5. Total forces in one dimension. When forces act in the same or opposite directions, okay, that's the definition of one-dimensional forces. That's dimensional forces. Ugly, ugly writing. Okay? The total or sometimes called net force, can be found by adding the forces if they're in the same direction or subtracting the forces. My writing is terrible. If in opposite direction. Okay. General idea there. Often useful to draw forces as vectors because they are vectors. Draw them as the arrows showing which way is going. So here we have example 1. Okay? Going to clear this screen so we can go to example 1. Two workers push in the same direction to the right on a crate. So here's the crate. On the floor, you got worker 1 and worker 2. Pushing on the crate in the same direction. The force exerted by worker, I'm going to work worker 2, is 150 pounds. Is that a good unit for force? Yes, pounds is a unit of force. Excuse me, got the hiccups. The force exerted by the other, which is worker 1, is 175 pounds. The only reason I did this way is I drew this line longer. Okay, so there's your force of the other. Find the net force exerted. Pretty easy, huh? The net force. Now this is not normal force. I'm going to use little n for net force. Capital N is normal force. What's the net force by the two workers? 325, what you say, pounds?
Yes.
Perfect. Because this is a significant digit there, both the answer should be in 3 significant digits.
Why does it have the bar over the 0?
Because that means it's a significant digit. Most of the time, a 0 before a decimal place is not significant. If it has a bar over it, means it is.
Okay.
Yeah. Good question. Okay? Now, there was something else I was going to say here. Because it's a vector, you need to give a direction to the right. Okay. Because both forces were to the right, the net force is to the right. Okay? Now, this time, the same two workers push the crate on the crate to the right. The motion is opposed by a static frictional force of 300 pounds. Which way is that pushing? Opposite to the way of motion. So this will be 300 pounds. And I've got to find it. There it goes to the left. Okay. Now, find the net force. I kind of hate they say static frictional force because you'll find out that you've exceeded that. So what is the net force now? Is what? I can't hear you. No, it's 300. I'm sorry. I slashed my zeros and that one came out ugly. Okay. Let's see if I can clean that up a little bit. Well, it didn't clean. Wrong thing cleaned. Okay. Okay. And because it's the second zero is significant, any zero in between significant digits is significant. So that's 3 significant digits. So what would be the net force now? Second? 25. In which direction? To the right. Because it exceeded the one to the left, so it wins. So that must have been a kinetic friction, because the other one, you still have motion. They said static, that probably should have been kinetic. Okay? Now, the crate in example 2 that we just did has a mass of, now what's the mass unit for U.S. customary system? Anyone remember? The mass unit for U.S. customary system goes back to what we did probably 2 weeks ago. Second? Slugs, exactly. So the mass of this crate is 5.00 slugs. No one uses slugs, so it doesn't even have an abbreviation. You have to spell it out if you're going to use it. The question is, what is the acceleration of the crate when the workers are pushing against the frictional force? What you think you're going to use? Any equation that relates net force, mass, and acceleration. Yes, the net force is equal to the mass times acceleration. And what was our net force with the friction involved? 25 pounds is equal to 5.00 slugs times acceleration. Now, I wish I had thought ahead, okay? Because if I had thought ahead, I would have not written that as pounds, even though that's what it was. It's 25. And by the way, here's another timeout here. When you're multiplying or dividing significant units, you go with the least number of significant units. When you're adding or subtracting, if you had 325 subtracting 300, remember, that gave you 25, you don't put a 0.0 there. You use the unit that you're dealing with. Most significant is 5 pounds, 0 pounds, so you go to the nearest pound. So that's 25 pounds. What you did when you subtracted, you lost a significant digit. Nothing you can do about it. Okay? So, I would have written that pounds as, anyone remember the fundamental units for pound? It's a weird one. Pound is a slug foot per second squared. That's what a pound is. A slug foot per second squared. So how do we find A here? Acceleration, that's what we're looking for. It's pretty easy. If these two are multiplied, how you undo multiplication? Divide. So divide both sides by 5.00 slugs. Okay? Units are your friends. Keep up with them. This slug cancels out that slug. 5 will go into 25 how many times? 5. But you got 2 significant digits here, 3 down here, so you go with the least significant digits, 2. So that's 5.0. And your units? Feet per second squared. 5.0 feet per second squared. So there's another example of how to keep up with significant digits. When you subtracted, you dropped from 3 significant digits to 2. Even though that 5 had 3 significant digits, your answer here can't be any more than 2. So it should be 5.0 feet per second squared. And that's why the book shows it 5.0 feet per second squared. See that? All right. Now, all right to erase this one? Okay. All right. Example 4. 2 workers push in the same direction on a large pallet. The force exerted by one worker is, okay, so I'm just going to draw something here to be the large pallet. So one worker pushes with a force of 645 newtons. The other worker pushes with a force of 755 newtons. The motion is opposed by a frictional force of 1175. So you have a frictional force opposing the motion going in the opposite direction of 1175 newtons. Find the net force. This is so similar to one we did earlier. I don't know why they did it again, but it's fine. What would you do? And I just randomly drew them right and left, so we'll stick with that. What do you get? Okay, you add those two together and you get 1,400, don't you? Newtons, but then you subtract this from it, 1175 newtons, and what do you get? 225 newtons. And I'm happy with 3 significant digits there. Okay, 225 newtons, that's exactly right. So that's your example 4. That finishes 5.5. So I would say good things to do for homework. Any of the odds 1 through 5. Any of the odds 7 through 13. Okay. Now those are the last with any exercises on, but there is one more section, and this is 5.6. So I think what I'll do here is discard this and go back to my other one, because I think that's the last slide here. Okay. Now, 5.6, okay, if you remember, way back, we did the law of inertia, Newton's first law. An object tends to maintain its state of motion unless it's acted on by an unbalanced force. If it's at rest, it stays at rest unless it's acted on by an unbalanced force. If it's moving in a straight line, constant speed, it stays in a straight line, constant speed, unless it's acted on by an unbalanced force. Newton's first law, law of inertia. Second law was very similar. If there is an unbalanced force called a net force acting on it, and we just use that one, then it accelerates or changes its motion. Okay? It either speeds up, slows down, or changes direction. All of those are accelerations because you're changing velocity, and velocity is a vector. So when you speed up, that's changing your velocity. When you slow down, you're changing your velocity. When you change direction, because velocity is a vector, going from there to there, you had a change of velocity. That was the second law. Then we got off onto weight and those kind of problems, and when we did all these other things, we never got to the third law. The third law is this one in 5.6, and this is the law of action and reaction. Okay? Now, this first figure actually is a figure for the problem set that we just had, I believe. Yeah, that was the figure for number 7 in 5.5 problem set. So that's why that's up there, because that's not action-reaction. 511 is, but we don't have 511. They show 512, which is also action and reaction. Not my favorite figure, okay? I don't particularly fond of showing gunfire. I don't even want to have gunfire happening, okay? So the law of action and reaction. Okay. And by the way, when Newton expressed this, at least I've been read or heard about it some way, he expressed it this way. He said, when I push on a rock, the rock also pushes on me. I pushed on the table, look at the indentation on my finger. It pushed back on me. That's action-reaction. Now that's different from the law of inertia, which was an object continues in motion. It's only talking about one object. The second law, talking about one object. If you do have a net force acting on an object, it changes its acceleration. It accelerates, changes its velocity, its motion. But the third law is two objects. If I kick on the chair, probably it's going to hurt my toe too, because the chair is exerting a force on my toe. Okay? Same deal. But it's always dealing with two different objects. Action, reaction. Okay? We call one the action object and the other, or the action force, and the other is the reaction force. Okay? And if you went back here, if you had these being equal to each other, this was a different problem. But if you had them equal each other, that meant the force of the ground on the tires is your reaction to the force of the tire on the ground, because now you're dealing with two things. This problem was dealing with something else, okay? But if you had that, then here's what Newton's third law says. Yuck. I think I'll go back because there's not enough room to write here and write on this slide. Okay. Newton's third law. For every force, let me get my pen back. Okay. Law of action and reaction. Okay. For every force applied by object A to object B, that's the action. Okay, I push on the table. I'm pushing on the table. That's the action force. There is an equal and opposite force exerted by object B on object A. Okay, that's the reaction force. Okay. Before we get to the firing a bullet, which is a good example, but have any of you ever been in a lightweight bass boat? Aluminum boat, maybe fishing or just paddling around? No? Too bad. Oh, you have, right? All right. Now, what if your buddy didn't tie up the boat too well and you go to step off the boat? What happens? It goes back and you may splash into the water. Why? Because when you push off the boat, if it's not tied up well, then you push on the boat and the boat moves and you splash. Okay? They do that in cartoons too, a lot. Okay? That's because for every action there's an equal and opposite reaction. Okay? You push on the boat and the boat moves. Okay? Now, I was on an aircraft carrier in the Navy. And if they had forgotten to tie that up, they'd have been in big trouble. But even if they had, if I stepped off the boat onto the ladder that went down, I'm not going to move it at all. Because it is so incredibly big, okay? It's not going to sense my push at all. The lightweight bass boat will, okay? So that's an example, probably not a great example, of Newton's third law. The one they show here is probably a better example. I just don't really like it too much, okay? And that's firing a weapon. Have any of you ever fired a pistol, a rifle, shotgun, anything like that? Okay, a few of you have, okay? What happens when it fires? It kicks, okay? Now, I was in the military, of course, had to fire weapons then. Fortunately, never at anybody, fortunately. But when you were firing, especially a high-powered rifle, you didn't hold the rifle off your shoulder. If you did, especially if it was a high-powered rifle, you're probably going to have a separated shoulder, because that little bullet coming out of the end, you've exerted, when that explosion happens in the cartridge and that powder goes off, that bullet is fired out of that with an enormous force. And guess what? The gun kicks back with a pretty good force too. If you don't have a separated shoulder, you're going to have a huge bruise. Okay? And probably a bruise and a separated shoulder. But if you hold the gun tight against your body and fire, then now your body is part of the system, so you have more mass, the gun and your body, so you do still feel it, but it's not nearly as severe. Okay? That's an example here, and that's exactly what's happening here. The force of the bullet, the action of the bullet outward, and we'll get to this, no we won't, okay? But the force acting on the bullet, sending it speeding at a huge rate of speed, an enormous acceleration, even though it's a pretty small mass, that's quite a bit of force. You have that same force back on you. Now, when someone is firing in rapid succession, you'll almost always see the pattern go up, because if they're firing in rapid succession, they don't have time to get their hand back down again. And that's why the idea of arming teachers, I think, is a terrible idea. If they're not trained, then they're going to fire once and maybe toward the person they were going to shoot at. The next one's going to go awry, and who knows who's going to be in the way of that one. So handguns are notoriously inaccurate. So terrible idea to, in my mind, to do that. Now, how we express this, the force one, this is gun on bullet, that's this force, same force, equal and opposite, bullet on gun. So in other words, the force backward reaction on your hand is equal to each other but opposite in direction, because they're vector quantities equal but opposite. So that's the same force backwards, just in the opposite direction. Okay, and that's really all there is they do. No exercises or problems to do on that one. Now, in your text, there's try this activity as well as a physics connection there. And let me just go over those fairly quickly with you. If you had And they call it a balloon rocket, and they do a better job of it than what I'm about to describe. But if you blew up a balloon with quite a bit of air in it and then released it, what is it going to do? It's going to take off and go. Now, it'll probably go all over the place as opposed to this one because you have a flexible nozzle. The end of the balloon does this, so it goes in all over the place. Well, why is it doing that? Because the air is rushing out this way, force, and it's pushing the balloon in the opposite direction. That's the action force, the reaction force. And every time the nozzle twists, it changes its direction too, because it's always in the opposite direction. Okay. Now, so balloons operate that way. Okay. And actually, the earliest flying machines were balloons, blimps. Okay. Next, after that, they had propeller planes, starting with the Wright brothers and then others that followed after them. And those, the propellers are pushing the air backward, right? Propeller turning, pushing air backward, which then pushes the plane forward. Action, reaction. That's how propeller planes fly. Well, after propeller planes, this was between World War I and World War II, we came out with jet aircraft. And how jet aircraft do is the jet engines fire that exhaust in very rapid things out the back, pushing the plane forward. Action, reaction. Okay? Same deal. And then what they show here, the shuttle launch, the action is the exhaust firing out the back of the booster rocket, and the reaction is pushing the shuttle upward. Okay? So there's your action reaction again. So just about every kind of flight, motion on water, just about everything, action reaction. When you swim, you push back on the water pushes you forward. Action reaction. Always two bodies involved. Your body, the body of water. All right. End of the chapter. There is a section, glossary section, making sure you understand the verbiage so you can work the problems. There's formulas listed there. They only list 3, but remember, just about every formula, you can make 2 or 3 other formulas from it. And then there's some review questions that are pretty good to think through, but the really good problems to do are the review problems, and those are the, again, I think it's the odd numbers that are in the back of the book, any of the odds 1 through 17. All right, that finishes chapter 5, and that means we're ready for the test in chapter 5. Now, surprisingly, you all decided that you wanted to have take-home tests, which I guess I'll put up with, you know. So here are your tests. And I think I told you before, I found that the PowerPoints on this book are pretty weak. The test bank is also pretty weak. But it's okay. The questions are good. They sometimes the answer keys and the things, they leave some problems. And this one has at least one error in it. I wish the people who left would have remembered to give them the test before they went, but they just sort of left. Will any of you see either of the ones who left? What's that? Oh, and you're going to take a picture. Okay. Okay. And the person who's missing, one we haven't seen, so I'm not worried about her too much, but Vega. Anyone likely to see her? Okay. All right. The one error on this, number 7, and you see I've corrected it. A small railroad engine is able to exert, and they put 17,500 pounds of pulling force, and then they have the problem with the coefficient of friction and all these things, and how much many rail cars weighing 45,000 each can this engine pull on a level track? When I worked the problem I said, it can. Okay. And I worked and finally looked at the answer and worked backwards and found out they left off a zero. That should have been 175,000 pound pulling force, not 17,500. So that's what that is, 175,000 pound pulling force, and then how many rail cars?
Do you want us to actually write on these in like
You
staple?
may if you want to. I would say you probably would be better off having some additional. You can write front and back wherever you want to, but the odds are you're going to be in better shape if you have.
But you just want our final answer.
Oh, your final
on this
answer
page.
here.
Okay.
Exactly. And I think all those are fairly straightforward there. I'll just give you a hint. Number 5 is both looking for a number. Oh yeah, it says it. Find the net force including its direction. So you're going to have to write a number, a unit, and a direction on it. So that might be a little crowded, so you can write above and below or take up the space in between. Okay. Any questions? All right. If you need it, you can have 2 weeks to work on this. If you finish it in 1 week and want to turn it in next Wednesday, that's fine too. But if you need 2 weeks, or if you go home and say, hey, I don't know how to approach this one, I will not work one of these in class. But if you find anything in the book similar to it, I'll work those. Okay? Now, that was chapter 5. The next chapter, if you recall, in our syllabus and description and everything, is chapter 8. So let's get out of chapter 5. Okay. And go to chapter 8. All right. Now, wait a minute here. What happened to it? It just disappeared. So let's go back to this and see if we can pull that up again. Chapter 8. I hit the wrong thing. There we go. Maybe. This is strange. Okay. Trying to find the edge of it. Here we go. It's not coming up. And I don't know why. Let me try it again. Chapter 8, PowerPoint. There we go. I don't know why it wouldn't come up the first 2 times. All right, chapter 8. Any questions on chapter 5, by the way? Okay. The best thing to look at for the test are the problems at the end of each section and the one at the end of the problems at the end of the chapter. Okay, let's go from current slide. Okay, chapter 8 is dealing with 2 concepts. Chapter 5 was pretty much forces. This is work and energy. But you'll learn that work and energy are basically almost the same things. Okay? Work and energy have the same units. They're measuring the same kind of quantities. Okay? And that's what we're dealing with in chapter 8. Okay. Now, chapter 8 starts with this question, what is work? in the phrase that it says here, the common idea of the definition of work is quite different from the technical definition. We're dealing with the technical definition. We often associate work with physical or mental effort that leads to fatigue. The technical definition is much more limited, okay? And I'll give you, I guess we ought to give the definition first, okay? So let's go to that. Okay, now this is, we don't get to that until a couple pages over, so let's go back to this. Okay, go from current slide here. Okay, if I can get my pen from being trapped here. The technical meaning of work requires that work must be done by one object on another object. Okay? Now they give a couple of examples. I'll give you this one. Let's go back to this table. This time I'm going to jam it up against the wall. Okay? Now I'm going to push on this table. And I can push and push and push till the cows come home. Do you think I'm going to move that table? No. Now I can sweat and grunt and cramp my muscles and all that kind of stuff. Have I done any work on the table? No, because the table hasn't moved. In order to do work, you must have motion. So all the expense of energy by my, by my muscles and the sweating and the grunting and all that, doing no work if the table doesn't move. Okay? So, that's what it says. Work requires that, sort of a double meaning. The meaning of work requires that work must be done by one object on another object. If I were driving a stake into the ground, even if I move it just a little bit, I'm doing work on the stake. If I hit against a rock and drive and don't move it at all, I'm not doing any work. Okay? Work requires a displacement. Work is done when a force acts through a distance. So there's your definition. Work, let me get my pen back. Okay? Work is the product. What operation does that suggest? Product of the force. What operation does product mean? Say again? Multiplication, exactly. The product of the force being applied in the direction of the motion. Okay? And the magnitude of the displacement. Okay. Pretty ugly writing, but there it is. Here is the formula that says that. Work, capital W is work, is equal to force times displacement. I really don't care for the S part there, but the book loves it, so that's what we'll use, force times displacement. Now, they don't put the time sign in there, but I did. It's okay with or without it, but force times displacement. The product of the force. Now, get this. The force in the direction of the motion. We're going to hit that later. That last slide you saw with the angle in it, that was what that was referring to. But let me first give you this sort of dumb example, though it didn't seem so dumb at the time. All right. When my wife and I were looking to buy the house where we currently live, we were in a little 2-bedroom, one-bathroom bungalow. We have quite a few family members that would come through town periodically. That would get pretty cramped pretty quickly, okay, especially the one-bathroom part. We'd sleep on the sleeper sofa in the living room and stuff like this, but the bathroom was really tough. They had good-sized bedrooms and stuff. We really liked the house, but we needed something a little bigger. So we found this place, and it was in the area of town my wife absolutely loved. Fortunately, she likes older things, so that's why she keeps me. But she likes older houses and antiques. It's not that funny. Okay, antiques and things like this, so she keeps me too. Okay, and we found this house, and it was just really good. Now, one little problem with it, though. Some previous owner, when the house had been built, it was built on a hill, but they had leveled this one part, built the house. The front yard went down this way, but the backyard went up this way. Okay. But someone wanted a little bit more room, so a later owner had built a screen porch in the back and also a family room in the back. But when they did that, they dug into the hillside in the back. So it gave the house sort of a squatting look, because the backyard came right down below a window, and they were narrow windows too, and then in front it was big windows and stuff, and it made it look like the house was squatting. Well, I didn't care so much on the look, though it didn't look to me all that appealing, but my wife's the aesthetic part, I'm the more practical. I still saw the hillside here. The water ran rain, stuff right against the wall of the house. And I didn't care for that too much because that's hydraulic pressure on it. And I'm sure it was built well and stuff, but over time that could have an influence. The second issue was, like I said, the soil came right up to the windowsill. So the soil to ground displacement was really close. In fact, it seemed like it was in touching. And when you're in the South and have soil to ground contact, you can have termites. Well, sure, I'm certain they used treated lumber, which would resist termites for many years, but you see that treatment will bleed out, especially when there's lots of moisture, and in the South we have lots of moisture. So in time, that was probably going to be a problem. So I said, Karen, you know how it sits like that. I knew she liked the house. I liked the yard. I liked everything about it. But I said, I think we're going to have to do something about getting the water flow away from the back of the house and also reduce the wood-to-ground contact. And she said, good. I wanted a patio anyway. Not exactly what I had in mind. I had a small job just getting the water away from the house. She had this big job digging out a patio. So that summer, it was my first summer teaching when I was at Western State Technical College, which is the campus of Lawson and Vesper now. It was my first year teaching there, and that summer I only had part-time work. I was a new kid on the block, so we didn't have enough enrollment for me to be full-time, so I taught 2 classes twice a day and had the other 3 days off, And that was for the first 5 weeks. There were many term classes. Second 5 weeks, I was off completely. So that became my summer job, digging out the patio. Okay. And so I launched into it with a pick, a shovel, and a wheelbarrow. And we also had this other issue, and decided one. I had to do something with the soil, so previous owners had also poured a slab in the back of the yard. And it was sort of an ugly slab, just a slab. It wasn't very well finished or anything else. And we asked the realtor, why did they do this? He said, I don't know, but one of the neighbors said he thought so that the kids would play on the swing set and not get their clothes dirty. And I thought, oh yeah, falling on concrete would be much better than getting your clothes dirty, wouldn't it? So I couldn't figure it out. So anyway, so I had them break up the concrete slab. And they brought in a big old hammer drill on a bobcat and said, shoot for about 1 foot square pieces. And so I used those pieces to build me a retaining wall, sort of terracing, and put the soil behind the retaining walls. I did a series of those down the hill because we were on a hill, remember. That's on the side yard. So that was my summer job, was digging out the patio. But then I got about halfway into the patio and suddenly hit this monstrous boulder. If you've ever done any digging in the Birmingham, Bessemer area, you're going to hit rocks, okay? Red Mountain, we're right at the foot of that, okay? Is going to hit rocks, and boy, did I ever. Because this boulder was there, and I kept digging and digging. And finally, I mean, the thing was about this big around and at least that tall, okay? And I dug around it and around it and around it, trying to get under it. Thought finally I was getting close to getting under it, and then I was trying to move that thing. And I would get cheater bars and rocks under there, fulcrum levers, doing everything I could to budge that thing. And I pushed and pulled and sweated and maybe said a few words. What? No, I wouldn't do that, you know. And anyway, how much work was I doing on that boulder? Not a bit, because I had zero displacement. Even though the force was enormous, I felt like, that I was exerting on it, and I certainly was sweating and grunting and all sorts of things, but if I did not displace it, I was doing no work. Don't come and tell me that while I was doing it. I didn't want to hear it, but by the physics technical definition, I was doing no work. Okay. Now, they talk about moving a crate. If you push or pull or lift and it's too heavy, you don't move it, you're doing no work. No matter how much effort you're putting into it, you're doing no work. But if you do get it to move, then the work you're doing is the product of the force that you exerted times the distance you moved in the same direction. That's an important part of it. Okay? Now, let's talk about the units for work. What's the unit for force? Pick it. Second?
Newton and pound.
Okay, let's start with Newton in the SI unit. What's the unit for displacement in the SI unit? What do we sometimes call the SI units? Other name for it. Starts with an M. Metric units. What does metric come from? What's the root word? Second? Meter. Metric unit, meter. That's what the unit of displacement is, a meter. And a Newton meter is, it has its own name, and that's a joule. Why is a capital J? Named after somebody. His name was James Prescott Joule, born in England, and he did a lot of the early work showing the relationship between work and energy. He was quite a bright fellow. However, he was born at a time when England was just beginning to change very, very slowly. Before this, it had been a feudal system. You had the lords, the landowners, the rich, and you had the peasants. Okay? And they did the work for the lords, the rich, the landowners. Okay? Still have this in name also. I just was hearing on the way over here. They have two houses of their parliament. We have the House of Representatives and the Senate. What are they called in England? Does anyone know? The House of Commons and the House of Lords. The House of Commons are elected by the people. The House of Lords are appointed or inherited through their ancestry. Okay? They don't pay as much attention to this, but at the time that Joule came along, very separate. You had the honchos who had the good education and everything else, and you had the poor people who typically didn't. Okay. But things were changing. Actually, the generation before James Prescott Joule. His father was a brewer. He made beer and other spirits. And about this time, things were changing, and now the middle class was coming up. And boy, the people who made beer and spirits, they made money, okay? And soon this middle class was outpacing the lords and the rich. Well, being the son of a brewer, no one wanted to pay any attention to him, especially in the royal societies. But he was such a bright, bright character that one of the lords, and we'll run into him a little later, his name was William Thompson, and he also had a title. He was Lord Kelvin. He was also, this is really rare, a brilliant scientist. And Thompson recognized the brilliance in Joule's work. He said, look, bring him in. He deserves recognition by the Royal Society just as much as any of us do. So he was admitted to the Royal Society. James Prescott Joule. The unit for work and energy is named after him. Now, in the U.S. customary, what's your unit for force? Pounds. What's your unit for displacement? Foot. Okay. And we don't have a special name for it, so we call that a foot-pound. Okay. We just reverse the order and call it a foot-pound. Now, a few of you may have used a wrench before. I kind of doubt it, but you may have used a wrench before that was scaled in foot-pounds. Any of you use that? Probably not. That wrench name is called a torque wrench. But a torque wrench, even though it's measured in foot-pounds, you're not measuring work. Okay? And here's why. The work is the feet that you've displaced something times the force in the same direction. What a torque wrench is measuring, and this is what I was kind of like what I was trying to use on that big old rock, but not quite the same. If you have a nut or a bolt that's frozen, you can't get it to break. What you do, what I said, you put a cheater bar on. So you have a long distance that you're exerting the force, and sometimes you can break it loose. The reason for that is the force that you're exerting is this way, the displacement is that way, that produces torque. See, the force is perpendicular to the displacement of that's torque. It's still force, pounds, displacement, feet. Foot-pounds is what you measure, but it's a different kind. That's a twisting force, which is actually a vector, whereas work is a scalar. Even though force is a vector, displacement is a vector, this is called a dot product. That you multiply two vectors together with a dot product, you get a scalar number. Work is a scalar quantity, not a vector quantity. Whereas torque, that's a vector quantity. So don't confuse foot-pounds here with foot-pounds of torque. Not that you will, because that's a chapter we're not going to do. Okay? So you measure that in foot-pounds. Work is not a vector quantity because it has no particular direction. It's a scalar quantity only with magnitude. So let's do example 1. How are we doing? Yeah, we got time. So let's do example 1. All right to erase this? Okay. Find the amount of work. That's going to be the W. That's what we're looking for. Done by a worker lifting 225 newtons of bricks. So 225 newtons of bricks, that is a what? Newton measures what? What entity does a Newton measure? We just were talking about it. Force. And 225 newtons of bricks would be the weight of the bricks. So that's the force due to weight. due to the gravity, okay? And he is lifting that a height of 1.75 meters. So that's going to be his displacement, 1.75 meters, okay? He's lifting it, okay? Now remember, the force, the work has to be the force in the same direction of the displacement. So if he's lifting the bricks, he's lifting upward, force is downward, so his force has to be in the opposite direction of that. So yeah, the displacement's up and the force is up that he's having to exert to overcome the weight. So yeah, that is in the same direction. So what would the work be? What's the formula for work? Force times displacement. So this would be 225 newtons times displacement of 1.75 meters. And by the way, about what is 1.75 meters? 1 meter is about to here, 0.75 would be about, so he lifted it to his shoulders. And that's what it shows in the book, about 1.75 meters. Okay, in the same direction of the force, okay? And if someone's got a calculator, I'm not about to try to do that in my head. Say again?
393.75.
And what unit? Say again? Newton meter. That is one way you could express it. What is a Newton meter, though? Say again? Joules, exactly. Or joule. Okay, okay. It's not rounded to a whole number. I was going to get to that. Good catch there. How many significant digits here? 3. How many here? 3. So you count 1, 2, 3. Look to the right. Is that greater than 5? 5 or greater? Yes, it is. So you bump this up to 394 Newton meters or joules. 394 joules. Is that what they got? Good for them. Okay. All right. Good deal. This time, we've got a worker pushing a cart. Okay? That one, he was just lifting the weight upward. Okay? This time, pushing a cart. Okay? Now, I think I'll clear, all right to clear the screen? Everybody got it? Oh, here's another thing I wanted to do before I do that. Okay, a Newton is a derived quantity, remember? Anyone remember what the basic unit for Newton was? Remember, it's a mass times acceleration. That's what a force is. So it's a kilogram meter per second squared. So you multiply that by another meter. So the basic unit for a joule is a kilogram meter squared per second squared. That's what a joule is or a Newton meter is. I just want to show it to you in the basic units. You can't get any simpler units than that. Newton is a derived unit, joule is a derived unit, but kilogram, meter, second, those are basic units. Okay, enough of that. There's a reason for I did that, so we'll come back to it later. All right, this time a worker pushes a 370-pound cart a distance of 30 feet by exerting a constant force of 40 pounds as shown. How much work did the person do? Now, I'm not going to draw mine as pretty as his, but here's what I'm going to do. Here's the cart with the load on it, load of stuff on the cart. Here's the wheels on the cart. The worker here is pushing with a force of 40 pounds. And that 0 is significant. Okay? My wheels look like they're going to fall off, but hopefully they won't. Okay, he's going to push it a distance of 30 feet. and that 0 is significant also. The weight of the cart, which way does the weight go? What? Always toward the center of the earth. This is the force due to weight, and that is 350 pounds. That's how much all these rocks or blocks or whatever it was on his cart. It's a heavy load, 350 pounds. He pushes it 30 feet with a force of 40 pounds. Okay? How much work does he do? So we're looking for work. It's what? I can't hear you. A little louder. My hearing's terrible, sorry. It's what? Okay. What is the formula for work? Okay, I know, but I'm asking what's the formula for work? Force times displacement. Okay? That's multiplying. Okay? That was, I wanted to get your answer to my question so I could give you the answer to your question. However, what force are we talking about? Which force is doing work? The 40 pounds, because it's in the same direction of the displacement. This is not doing any work. Okay? Sure, that's contributing to it. That's why he had to push with 40 pounds of force. But this is not doing any work. This force is perpendicular to the displacement. It's not in the same direction. So the force you use here is this force, the force of his push. So this would be 40 pounds times 30 feet. And what would that be? 100. Okay, say that again. Say again. 1,200. What unit? Usually we put it as foot pounds. Pounds feet is fine. You can write it that way. Usually we put it as foot pounds. Okay. How many of those zeros are significant? Second? Okay. No, neither of them. How many significant digits here? That one's significant. Oh, that's what you answered. Okay. And how about here? 2. So you only do 1, 2. These are not significant. You don't throw them away. They're important. But the answer is 1,200 foot-pounds. Don't cross them out, but don't put a bar over them.
Why don't you?
Okay? Because you only have 2 significant digits here, 2 here. The product can only have 2. Those 2 are your only 2 significant digits. Those last 2 zeros are placeholders.
So why is your answer not 12?
Because there's no decimal in there. It's 1,200.
But you're saying the zeros.
They're there as placeholders. That's for tens and units of foot-pounds. But, so, I mean, it's 1,200 is the answer, but only these 2 digits are significant. These 2 are not. If that had been 1,230, you'd have rounded up and made it 1,200. I mean, you wouldn't have rounded. Okay. Okay, no. Okay. If this would have been a 45 here, okay? 45 times 30 is what? Second? 1,350 foot-pounds. Okay? What you would do then, 2 significant digits, count 1, 2, look to the right, that's a 5, that means you increase this by 1, that'd be 1,400 foot-pounds. You have to have the 2 zeros there because it's 1,400, you know, but they're not significant, so you don't put a bar over them, okay? This is 1,200.
1,340, you would just make it 1,300.
Yes, exactly. Okay? And this was 1,200, so what do? I shouldn't have really made that mark there. What I was trying to say is they're not significant. You count 1, 2, look to the right, it's a 0, you drop it. I mean, you don't drop the 0, but you don't round up. So you just leave it 1,200. Okay? Good deal. Does that make sense? Let's see how the book did. 1,200 foot-pounds, good for them. Okay. How are we doing on time? You don't think we have time for the next one? No! Oh, man. Okay, we'll pick up then. Somewhere here I had a pencil. We'll pick up then with this illustration here. And I think you can start doing some of the homework exercises on page 206 and 207. You can do, now here's a problem, folks. If you look on page 206, they number 1, 2, 4, and 6. They left off the numbers for 3 and 5. The ones underneath the 1 are 3 and 5. Okay, so you can do any of the odds 1 through 5. You might be able to do 7. You might be able to do 9. You might be able to do 11. Hold off on that. We'll worry with the rest of those later. Go through 11. And we'll pick up there next time. Good deal.